All right, thank you. Yeah, so
Oh,
title.
we're recording, is that right?
Yeah, I think Josh is doing something too.
Something too. Okay.
We'll see how it goes.
Then I might just let you. Okay.
All right, so yeah, title of my talk, Nix sucks and everything else is worse. So how many of you even know what Nix is, by chance? A couple of you guys.
Unfortunately.
Yeah, Josh knows. So the subtitle is Building Better Software Supply Chains, which we'll get into the meat of. But essentially, Nix gets very close to accomplishing this. But, well, I mean, it started as a research project, so kind of didn't really evolve from there, in my opinion, in terms of like UX, which also translates into some serious performance issues. Yeah, anyway, who am I? I'm Tim DeHerrera. I have been using Nix since I think about 2017, somewhere around there, and started contributing to the ecosystem maybe a couple years later, 2019-ish. So yeah, this talk will represent almost a decade of very specialized expertise. So I attempted to sort of condense it and try to keep it relatable, but we'll see how I do here. So what is the high-level problem here? Well, essentially entropy, right? So this is something I think anybody who has used a computer has experienced. I remember a good example when I was a kid, reinstalling Windows over and over again. I don't know if anyone else ever experienced that. It was actually a really cool tool called Deep Freeze. I remember, I think it was like the first pirated software I used. So sorry about that, but yeah, it would basically freeze the Windows disk to read-write and then do like a temporary overlay so that your system didn't get crufty over time, and you could like reboot. So in a way, at least NixOS is kind of like the programmer's wet dream version of that, but when it comes to actual programming, the problem actually sort of amplifies because you start ending up with dependency conflicts. The big one, the one that I'm really trying to address, is supply chain attacks. So you can do everything on the code side to try and make sure that you're writing quality, secure code, but if you're then stuffing that into a centralized registry that you don't have full control over, there's a lot that can happen in between. And then also when you're developing, obviously you need development environments, and this problem translates to non-reproducible environments when you're trying to actually build your code. It works for me, send it to Zach, doesn't work for him, who knows why, right? So yeah, this is basically a universal problem. Some operating systems do better than others, but let me see. The purported solution for a long time has basically been package managers. Who has used a package manager before? You guys know? Okay, so that's what Nix calls itself, is a package manager. I think that's a bit of a misnomer, but so if you don't know what a package manager is, it's basically like an app store, high level. Just helps you manage and install software on your machine. It's supposed to help you manage dependencies, but we'll get into why it's not really the greatest at that. And then obviously updates and uninstalling software as well. I have some demos to try and make this concrete. So the first demo is really quick to try and demonstrate why this is a problem. So we're going to demonstrate, we'll simulate installing software and watching how the environment changes. So basically we're going to install software A, right? And here if you look at the output here, you see two files were installed. We have software A and then a dependency that it depends on, lib dependency. So if we continue here, time passes and we want to install software B, which conflicts with A. So now we install software B, and if you notice, if you look carefully, lib dependency was updated to version 2.0, which may or may not be compatible with the version software A expects, right? And since these are all shoved into a shared library directory, then we can't really do anything about that. And then this just sort of compounds over time. You end up with random stuff in your machine mixed in. Someone could do something malicious. You could just not do very good. You could accidentally RMRF your machine.
Well, is everyone familiar with like this LS syntax?
Oh, yes,
for
I'm
a
sorry.
file system? I'm not sure. We might
Yeah,
wanna
so
go-
if I can just do a quick demo here. So this is like the actual disk right here. So we're changing what's happening in between. And this, I'm using an actual folder to like sort of simulate. These aren't obviously just fake files, but yeah, so over time, this obviously compounds. If you think about the thousands, tens of thousands, hundreds of thousands of files on a system, shared libraries, this can become a really big problem very easily, hence reinstalling Windows.
So we're looking at the right-hand side. So we have some information. We have like the permissions are on the left, and then we have like the user information, and we have like the date it was last modified, and then we have the name of the files.
Yeah, all this stuff is kind of irrelevant, and I think that's probably getting picked up from my Zeke configuration. So this is the main meat of it right here that I'm trying to demo. But yeah, hopefully that makes sense. If it's not clear, maybe I should clarify any questions now.
So and right now, it's just over time we're seeing that there's more and more junk in our folder.
Essentially, yeah. And so there you go. Software A might not work anymore because we changed its underlying dependency without really notifying it. So if we actually try to call it, maybe it'll fail and complain or do something random. And yeah. So hopefully that sort of illustrated things for you.
Was that being installed via a package manager?
That was simulating sort of how package manager works.
Oh, okay, I got you.
So has anyone I've run into that a lot on my system, where one dependency says I need this version, another dependency says I cannot have that version, you have to have this version, and then you're just stuck. Right. Yeah.
All the time.
Okay, so let's say, raise your hands, who's gone through that? Like, okay.
So everyone working in software, right?
Yeah, this is a common issue. So this is like Linux distributions like Ubuntu and a lot of these other ones. That's one of the primary things that they're doing. Is they're managing repositories and trying to avoid conflicts. Because if they publish a conflict, then you're just
I'll go
you're in
back
trouble.
Well, I'm sure everybody with Windows has worked with .NET before, right?
Yeah, and that too. Yeah, exactly.
That's just
Oh,
as
God.
bad.
Yes. So anyway, so how do we solve this? Well, we're going to get into some basic cryptography. I'm going to give a demonstration so that hopefully the ideas that I'm going to go over make at least some sense. But essentially, we're going to talk about hashes, which is really at the highest possible level. It's just like a thumbprint of your data. So like an unforgeable string that tells you that this is the thing, and if you change the data, then it changes the identity, so you can tell if it's been modified. Critical, I mean, a lot of people talk about cryptography, they think encryption, but hashing functions are probably one of the most important things in our systems, otherwise we wouldn't even be able to keep track of anything, really. So, and then obviously from there is a very particular data structure. So a data structure is just like a general term for ways of organizing data. Like the file systems that you're used to using, opening files and folders, that's a form of data structure. Basically just a way to organize information generically. There's obviously programmers are familiar with all kinds of different like lists and arrays and all that. But the important one here is going to be the Merkle tree. And it's honestly not that complicated, but if you don't understand some of the basics, it can be kind of like over your head. So I'm going to give a brief demo of how it works, and hopefully it will make sense because it's going to be very important. So yeah, we're just going to give a brief demo of how the hashes work. So this is a demonstration. Maybe I should come over here. So this is our data. The word hello right here. And if we want to get an identity of that string, we run it through the SHA-256 hash function. There are a bunch of different ones, but it doesn't really matter for our context here. And then this long random string here is going to be its hash. The important thing is that if we change anything, even just a little bit, just add the word world here, for example, we get a completely indistinguishable, completely different hash function. And so in this way, we can sort of unambiguously tell when a file or any sort of data has been changed. And it's a generic function, so it works over any type of data. You could just give it random data, it'll give you a hash. So now we're going to try to explain how a Merkle tree works. So let's see here. So it basically is built of what are called leaf nodes, essentially, and these are going to be 4 demonstration nodes that we're going to build our tree from. Each one represents a file with some very basic text in them. So hello world, toolbar, random text. Each one has an identity that we talked about. And then, now this is where it gets interesting. So if we want to be able to identify groups of these files together without having to traverse them all and verify each individually, we can actually combine the data together and then hash that. And so this first branch here of the leaf nodes is going to be files 1 and 2 right here. Basically just put together and then ran through the hash function. So now we know that the combination of those 2 files gives us this ID. We do the same thing with the second branch for files 3 and 4. And in this way, you can then move on to the next step of combining all of your files together, essentially, which is known as a Merkle root. So this basically branches now the branch hashes together, which they both represent the entire group of files. So by hashing those together, we basically get an identity for the entire group. And this is a lot more efficient. The key thing is that this is a lot more efficient than running this over, like if we had like 10,000 files, for example. Hashing all of those is going to take a lot of compute resources, but just hashing like 16 leaf nodes is going to be a lot easier. So that's one way that, yeah, this is really actually important to everything that I'm going to talk about. So does anybody have any questions about this?
I don't know any of this, but beyond just what hashes are. So if you hash those files, do you have to hash those files first before you start combining them all the way down to become a Merkle group, or?
Yeah, so this is basically the hash of the hashes, right? So instead of hashing the entire file contents, we're hashing this string, or this text. String is what programmers call it, same thing. And then, so you combine these 2 hashes together, hash that, and then you get this, right? So that helps to avoid, like, if your file is like a gigabyte, or like, the bigger the file, the longer it takes to hash. So if you just hash the tiny little string, it's a lot more efficient. And then build up identity from there, so.
I have a question. So how do you, when you get down to branch nodes, combining the child hashes, what do you use as a delimiter to separate the 2 hashes? Or is there a delimiter?
You can, I mean, I think different formats do different things, but I think the typical thing is literally just to concatenate them. There's also fancier things like key derivation functions. We probably shouldn't get into that. It's not super relevant. I do actually use one in my code, but we won't get into that. But yeah, usually you just literally just concatenate them together.
Okay, I see. Thank you.
Yep. All right. Now the important thing about a Merkle root is that if you change even one of these files even a little bit, we are going to get a completely new hash. So for the root. So if we change file 3 here, what did we have before?
I think it's the best.
Yeah.
AAA.
Yeah, so we modified the string here, and now we have a new hash for file 3. And so since everything depends on the combination of hashes, it's going to change the branch hash, and ultimately, since the branch hash changed, it changed the entire root. So we will get into it on the next slide. Maybe I should just move forward, and then I can kind of get into it. But yeah, why this matters. You can verify all files by checking just the root. You don't need to do individual files, basically everything I just said. Get, for example, who knows what get is? Everybody knows Git, cool. So it's a version control system. For those of you who don't know, it's just how you manage your software changes over time. And then here I'm actually printing the Merkle root of my current Git checkout. So the current source code that I have is actually represented by a Merkle root. So all the code in my repository is currently identified by this string right here. And we'll go back over here. Now, we talked about our original problem here, right? Entropy. So there are tools that try to solve this. Go ahead.
Sorry, just going back. You said when you modify it, do you have to rehash it all, or does it auto-hash it itself, and that's when you
Yeah, so the algorithms are obviously try to optimize and detect what has actually changed and then only hash the changed branches, essentially.
Oh, okay.
So typically, I mean, you could do the naive thing and just hash everything all the time, but
So how is the structure being built? You says, I'm gonna hash those 50 files, make a leaf from a leaf to a branch to a tree. Who decides the structure?
yeah, so there's usually some sort of data model for whatever it is you're modeling. Like Git, for example, it is actually sort of like a graph database built on top of everything we just talked about. So in addition to having a Merkle root, it sort of has like this simple data structure where it points to the previous commit, is what it's called. It's basically an object that So commit is, it's not the code itself, it's like metadata about the code. And it almost works like a blockchain, if anybody knows how a blockchain works. Essentially points to the previous change, and then that one points to the previous change, and then all the way down, so that if you change something 50 commits back, it's going to affect everything after that, and the entire identity will change. So you know if somebody put something malicious in your history, essentially. Yeah, so how you use it, it's going to be very contextual, depending on what you're actually building. But yeah, it's just like a general cryptographic tool, essentially. Hopefully that makes sense. But yes, back to our problem of non-reproducible environments, essentially. There are a bunch of tools that have tried to solve this because, as Zach pointed out, it's a universal problem. It's a long-standing problem, and it causes a lot of pain and critically, in especially large organizations, security issues all the time. So we have things like virtual environments. Anybody use Python? You probably have used VN or Conda before. So first of all, it's language specific, so it really only works with Python. But it also doesn't solve our dependency conflict issues, and it doesn't really guarantee reproducibility. It just kind of creates a little folder that you can kind of pretend is like the only folder that exists. Containers is the big one. You guys have probably heard of Docker. It's kind of like the industry standard, right? The big buzzword for a while now, at least before AI. How about Kubernetes? Anybody ever use that? Painful, yes. So the problem with Docker is that it sort of bundles everything together into these mutable black boxes, which are not actually reproducible, and we'll get into that a little bit. And then we also have these tools called lock files, which this is really for developers specifically. Like if you want to have a bunch of dependencies for like a JavaScript app, you have a package lock.json, and essentially that is supposed to help you by keeping track of all of your dependencies and keeping a hash, like we showed, of each one, so you know exactly what your software is supposed to depend on. But the problem there is mainly that most of those tools, in fact, I think all of them, rely on centralized registries. So whatever your code says, it could be drastically different from what actually is being published and distributed. So there's basically a window for someone to inject arbitrary code, which is never a good thing. And they're also usually language specific. So if you have like a multi-language project, it can get very difficult. But we're going to do a brief Docker demo because I think Docker is the big one. And it's also sort of like a direct competitor to what I'm building. So it's kind of important to demonstrate why we want to solve this problem. All right, so Docker makes some big promises. You're supposed to be able to build once and run anywhere. No more works on my machine issues and complete environment isolation. But in practice, you have these base images that change over time. So as long as you don't change your image, then most of those promises will hold. But the problem is that how those images are being built is not reproducible. So as time goes on, it will change out from under you. Dependencies inside containers can still conflict, so there's no really resolution for that dependency management problem, which is really the core problem for software distribution. And then the Docker container itself is verified cryptographically, so it has a hash, but nothing inside of the container is verified. So that's why I say black box, because you have no idea what that hash actually represents. It could be fine, it could be everything in there is good, or it could be there's a malicious script in there and the outside doesn't really tell you anything about that. And so because of that, supply chain attacks are still possible. So
I wasn't familiar with the base images change over time with Docker. That's like
we're gonna do a demo of that.
Okay.
So, and this is exactly why a lot of people like Nix. So we have a very simple Docker file here. These statements right from here to here. I should have put some delimiters here to make it easier, but basically we're saying from Ubuntu, and then this is a tag that specifies which image we want to use. And this is the problem you're asking about right now. And then you're going to run some stuff. This is actually also a problem because the app is a package manager. It's the one used for Ubuntu. So you guys are probably familiar with it. But essentially, to answer your question, what's going to happen is that whenever you run this, it's going to check the Ubuntu registry at that time. And whatever's in the registry at that specific time, it's going to pull. So if you run this today, you'll get one container. If you run it a week from now, you'll get a completely different container because the registry is constantly updating. And so that's the core of the issue. And then here, you're just telling it what you want to do.
Well, and I guess I hadn't thought of the fact that a VM still has to be implemented, and if there's security issues, even if you're in Docker, right? Like how it's implemented can be changed from underneath you, right?
Right, and there's a lot that changes since you're building an entire system. Like when you're pulling apt, you're basically querying an entire operating system's package repository. So you could have, need to update your container because of one dependency, and then you pull in 10 more that have issues or break something, and there's really no way to keep track of that. So on the surface, this looks good. This is what programmers tend to like. They call it declarative formats, where you sort of specify what it is that you actually want instead of having to programmatically specify all the logic to get it. So yeah, as I just said, if you build this Docker file today, you might get Ubuntu 22.04, Python 3.10. Next month, you might get 24.04.4 and Python 3.10.13. And as time goes on, this will just change out from under you. And so this could cause breakages, security issues. And here we are just demonstrating this is what Ubuntu container is advertising right now. I just queried it on the back end. So tomorrow this will be completely different, and the next day and on and on. And this wouldn't be a huge issue, except that everybody always uses the latest tag. So just trying to simplify things.
Why is that hash so short?
So it's truncated. So it's actually longer. Yeah, it's just the default output of Docker. They usually truncate it to, typically they shorten it to the smallest amount of non-conflicting characters.
And I've run foul of this myself. I frequently run Microsoft SQL servers inside Docker containers.
Oh,
Microsoft only does compatibility with certain versions of Ubuntu, and it will not run in newer versions.
Right.
So latest works fine the day you made it 2 years ago. It doesn't work now. Obviously, if you tie it to a specific version, you can get past that. But
Yeah.
Docker on Windows is
Yeah.
nightmare.
Yeah. Docker anywhere but Linux is kind of a nightmare in my opinion. But so yeah, And then, as I said, we could have those very same kind of dependency conflicts inside the container that we demonstrated in our first example. So dependencies are changing as the container is changing out from under us. So it could be good today, and then a week from now we have a conflict, and we need to deploy our app, right? And so now we have to deal with this problem. Could take all day, could take 3 days. Maybe you'll get lucky and it'll only take you an hour. So, but you don't know, and that's really the problem, is that it's sort of unspecified how long it's going to take you to solve, and it could show up at any time. And then obviously supply chain attacks, which is really the big one that I am trying to address. So because you don't really have any window cryptographically into the contents, you could just throw anything in there and you wouldn't really know. So I think I've pretty much gone all over that, but we do have real world examples, like in 2021, the code conv breach, if anybody remembers that. Compromised Docker images were being basically maliciously code being injected into them and then distributed. Various examples of that. Somebody doing like a spoofing attack on typo squatting where they had an Ubuntu container with 2 U's, and if you accidentally typo, you get a malicious container. So just stupid stuff like that. And then Docker does do some things well, which is why it's sort of the industry standard. So as long as you don't change your container, the deployment is consistent. As long as you deploy the exact same container, it's going to deploy basically the exact same thing. It does offer runtime isolation, although this gets oversold a lot. I won't get into it too much, but you really can't rely on it for security. It's more just for sanity and avoiding conflicts. And it helps you simplify your distribution somewhat. As long as you know all your containers work, you can be reasonably sure that your deployment will work. But since the containers can change at any time, that's kind of iffy. And then just managing resources. The big thing for Kubernetes, for example, is that you can limit the actual CPU cores and the memory available to each container so that it can't just max out your entire system, which is obviously very important for large servers, things like that. Things that it is not good at is basically everything we already talked about. Reproducibility, so it's just going to change depending on the time of day. No dependency resolution, as we said, supply chain, and really no version management to speak of, other beyond those tags where you can give it a name like latest, but that's about it. That's not really a concise version specification. So we're going to get into a little bit about NIX from here. So NIX does build reproducible artifacts, and I'll try to demonstrate that a little bit. And then a lot of people are setting it up where they will build everything with NIX and then stuff it into a Docker container. So you can kind of create minimal reproducible Docker images this way. But this is it's still kind of complex as someone who has actually done it in practice. And in this, NIX is by no means a simple tool. Docker layers themselves can have issues. So the way they're stored, I've run into I've run into issues where layers will literally just fail for like random corruption reasons. It's very difficult to debug Docker's. I'm pretty critical of the Docker CLI, honestly. It's good for like high-level things, but if anything breaks, it's like very difficult to know how to fix. And then, yeah, if you're going to take something like Docker, which already has its own complexities, and then something like NIX and mash them together, you're going to create a very complex workflow. So this is what I'm trying to do, which is called Eka. The tool is called Eka. The format is called Atom. Basically, I'm aiming to provide sort of a package management that Docker lacks with security guarantees of NIX while hiding the complexity. So Eka, at least in the first draft, does use NIX internally, but it is abstracted in such a way that you can have other backends in the future. Basically, we just need a tool like NIX to be able to guarantee that reproducibility. But the important thing about what I'm building is that all of the complexity of NIX is abstracted so that only the team that has to worry about how to package your software has to worry about it. The way Nix works now, if for anyone who's used it, it's very low level, and I think we'll get into that a little bit, but
So with Docker, to address some of the problems that you have in your X's, to go backwards a little bit.
yes.
Doesn't Docker usually recommend using like static images? Where they say like, don't do your updates, don't query for this, but then the downfall is you don't have security updates, right?
Right, yeah, and so a lot of people don't do that too. It's sort of convention. So, and then there's also the fact that tags are not really a cryptographic identifier. So you could literally just change the image behind a tag and think that you're still getting the same thing. If you don't pay close attention, you don't really have any way to know.
Okay, so if people are depending on tags for Docker images, that can be changed.
Right, and mostly because people don't want to have to remember giant SHAs, right? So they want to have a human readable name. But then that sort of detaches it from the cryptographic layer.
So I'm surprised that Docker doesn't like start using digest for their images. That seems like that would be a big way.
Yeah, I mean, you can specify an entire digest for your image, but the problem is then you have to go look up the precise digest for the image that you want, and then you have to pin it to that. And then anytime you have to update, you have to do this, and then if you have 100 images, it's not really easy to automate. It's actually kind of the similar problem to what I've run into with Nix. But yeah, I think maybe...
Because a tag isn't guaranteed to always point to the same image, just like latest new.
Yeah, exactly.
You're trusting the Docker file that
All right, I think...
2.7 is always the same.
Yeah. Yeah.
So we will move on, but actually, does anybody have any questions about Docker though, just in case? I think we're all good. All right. So there are some tools. These are not package managers, unfortunately, but they kind of serve as an inspiration for what I'm doing. Some people may criticize my list here. I am by no means saying that these tools are perfect, but they do the right thing in the sense that they use Merkle trees to create essentially tamper-proof and decentralized systems. I kind of talked a little bit about how Dick does that already. And then, who has ever actually looked into how cryptocurrency works? Yeah, okay. You guys know everything here. So, yeah, it's basically very similar to the way Git works. It's a little bit more streamlined because it has to be a very linear ledger-like history. But yeah, we can sort of take some inspiration from these tools, which is what Nix does. So Nix basically has what it calls static build recipes called derivations, which this is where we start to get into the whole research project thing. In my opinion, derivations is a very poor name to describe this thing. It's a source of confusion for newcomers. It sort of illustrates, in my opinion, how it's sort of a lower level concern, and it's not something we should really be exposing to regular users. But Nix does the right thing in the sense that all of the dependencies are precisely specified, not as a black box like Docker, but individually. And so you can basically create a Merkle-like chain of identity. And so if you change, like, even if you have like a tiny little patch, 100 layers deep in your dependency change, and you change 2 little lines in that patch, it's going to change the entire identity of your final package. So you know for sure if anything at all has changed. And I could demonstrate it, but it would take us down a whole... So the important thing is like the high level understanding. And the way that it does this is what's called pure functions. So if you guys have taken like a calculus class, you learn about domains and ranges and how a function will always give you the same output if you give it the same input. And this is not always true in programming languages. So every programming language typically has functions, but they're not always pure in the sense that they can do a bunch of random stuff in the body of the function that it will change over time, like write to disk or delete something or corrupt something. So a pure function is something that can't do any of that. It's literally just a math function, like 2 plus 2, or 2 times x will always give you 4 if you give it 2. And I'm going to do a real brief demonstration of what these look like, so you can kind of see. All right, so we have like an example of a very basic traditional build script. That's literally just a bash script. So bash is just like, kind of like what I'm using here. I'm not using bash, but it's like a terminal. You can script it so that you can do things automatically. Here we're just calling a compiler called GCC and telling it to compile our little C program here. Even with a tiny little program like this, we already have problems because we are assuming GCC is installed. So if we run this script and GCC isn't installed, then we can't really go anywhere. This right here is specifying a math library, so if that doesn't exist, that's another problem. And then also, we have no idea what version main.c is or any really metadata about our software right now. So we have JSON formats. Who knows what JSON? So this is literally a good example of what JSON is. If you don't know, it's literally just a very simple data structure containing key value pairs. You can have lists. But essentially, we're trying to describe the same thing in a more structured format. So we give it a name. We can give it a version at least now. We're still telling it to use GCC. We are specifying the flags as a list. And then this time, we can actually give it some information about our dependencies, which is a little better. And we're telling it the source file we want to compile. Let's see. Oh, I think I deleted a section here. So let me go into why this isn't really perfect here, because we still don't have any cryptographic identity for any of these dependencies. We just know it's glibc, but which glibc? In this case, we don't even have a version. You could maybe throw a version on there and help a little bit, but then if you have another project that needs a different glibc, then what do you do? So this is how Nix solves the problem. And it has what's called a derivation. This is the format. It's like 20 years old, so if it was modern, if it was designed today, they probably would have just used JSON. But JSON wasn't really a thing back then. So it's sort of a similar language in that it's just a static, there's no programming, it's literally just a format to describe. The unique thing here, the important thing, is that this right here is a hash. So everything contained in this folder is identified by this hash right here. And that's sort of how it creates that Merkle tree of dependencies. So basically, it's kind of harder to read because it's all smushed together, but we specify the exact same thing, but everything we specify has a very explicit cryptographic identity. And I elide the hashes here because it's a lot of text. But just imagine hashes here where all the dots are. And then, yeah, this just sort of goes over everything. So the traditional script doesn't really give us anything. JSON gives us a little bit. It gives us a little bit of structure and metadata, but still doesn't do a whole lot for cryptographic verification. And Nix basically solves all the problems we've talked about. So we have a cryptographic identity. Haven't really gotten into pure functions yet. So this is a real Nix derivation that it just searched for on my file system right now. So this is just a real world example. If you see the actual hashes were specified for all the dependencies. And then the way that this actually builds is that it's just sort of, it has a calling interface. So Nix itself knows how to call into this. I think where is it? It's kind of hard to read, but there's a section in here called the builder. It's basically a script that it just calls with arguments that you specify, and then that will, everything here is tracked so that if it refers to anything else inside of it, then it will pull that in as a dependency, and that's sort of how it automatically creates your dependency tree. None of that is super important to understand, so don't worry if, if it went over your head a little bit. The important thing is that you have solved all the problems we've been talking about.
You should show Nick's tree on the page, the derivation, so you can
Oh, yeah.
maybe like
Yeah, that's probably a good idea, actually. Where are we at? Oh, doesn't want to copy. Too far. All right. Yeah, so this is actually inside of the package after it has been built. So this one is an environment, so it's basically just a bunch of links to other Nix derivations, Nix outputs. So we have regular file names, but they're actually pointing to highly specified outputs.
So, and that's with Nix, that's built into Nix.
Yeah, so this is built with Nix, and how it actually does that. We're going to give a brief, and again, not super important to understand, but just so you can have sort of an idea of how that works. Nix doesn't want you to actually write all of that by hand because that would basically be impossible and just create all sorts of problems that we just talked about. So it uses what's called the Nix expression language, which there's a nice little demonstration of here. It's very JSON-like. Some people call it JSON with functions, essentially. And so here we are just giving it a name, a version. The build inputs are the dependencies. And so it looks like we're just calling GCC here. But behind the scenes, this GCC is a very specific GCC with a very specific identity. And then we tell it how to build it like we did before. And then this is how to install it. And then basically Nix will interpret this into one of those static derivations. And then it will try to build the recipe. And so that's super high level. Nix is actually deceptively complex. So I just wanted to give a really basic example so we can try to avoid all of the irrelevant complexities. But like I said, the important thing is like pure functions. So because we can't have random functions doing random things, we can be very sure about what we are building. As long as we always give it the same input, then we can get the same output, which translates directly to the files on disk at the end of the process. It's declarative, which is again very much like the Docker file where we don't want to have to specify all of the logic, we just kind of want to give a description of what we want. And then everything inside of that Nix store directory that we saw is immutable, so it's read-only. You can't just go in there and start deleting stuff and changing things. Nix goes out of its way to try to make that very difficult. If you're like the admin of the system, then you can remount it as writable and do all that, but that's not always going to be easy or possible. And then, yeah, like we said, files are stored by their hash.
They're also globally readable.
That is, yes, not the best thing, which is part of something I want to solve, but that's a little bit further along than where I'm at right now.
Well, is that a problem?
Yeah, I mean, if you put secrets in
API key.
Yeah,
As long as you don't have LS.
that's that's another side effect in my opinion.
Said, grep. Basically,
Yeah.
you have no commands.
As long as you trust all users on the system, it's not a problem.
If it's addressed by the hash, you couldn't calculate what the file name is. So as long as you don't have a discoverability, you're fine.
But you can, I mean, if you have a shell, you can see the files.
Well, yeah. You would have to not allow visibility.
You would have to not allow the shell access, which
Yeah.
not what we did.
Yeah, so there are some problems with these expressions. So it's complex syntax, so it looks like JSON, but it's a lot more complicated than JSON. It's actually a branch of programming called functional programming, which is known for its difficulty. It basically abstracts out all of the ability to do any sort of mutation. But in computers, mutation is how we actually get work done. So like reading to the disk, for example, is changing something. So to express something like that in a pure language can be very challenging. Deep knowledge required. Like I said, I've been doing this for almost a decade now. So I'm very confident in my knowledge at this point, but I see beginners making the same mistakes basically over and over again. And it seems like there is really no way to get good at it but to just suck for a very long time. And it's easy to get wrong because of that. And then also because everything is so tightly coupled, you need thousands and thousands of expressions to actually build something useful. All right, so does anybody have any questions about Nix? I know it's kind of complicated, but fortunately, I just wanted to give you a high level of Nix just to understand why it's useful and also a little bit about why it's painful. And then this is just a slide that kind of describes how the Nix store works. Like I said, it's immutable, kind of everything we talked about, addressed by its hash. We can probably move on. So I did want to talk a little bit about what's good about Nix. Like I said, perfect reproducibility or near perfect. You can't really control what the compiler is doing, so there may be some like environmental randomness depending on how your compiler works. But other than that, you have a complete description of every single dependency, cryptographically unambiguous. And this has security implications, which are very positive, but the problem, in my opinion, is that it doesn't really leverage them effectively. And then it is an extremely large ecosystem. So if we just look at this graph right here, which I linked to in the slide, you can see this is a website called Repology, where you can sort of look at different repositories of software. And if you look all the way up here, so this is the number of fresh packages in your repository versus the number of packages total. And mixed packages is kind of all the way up here. This is the unstable channel. This is the stable release. But yeah, you can see there's a giant gap. So this is why everybody loves Nix, because it has everything, and it has everything unambiguously. You have a bunch of here like Ubuntu, a bunch of different Linux distributions. So yeah, this is one of the main selling points. But because of the way that the package repository is architected, it's also one of the main pain points, in my opinion. So what is wrong with Nix? This is kind of the core of my work, so I'll try to explain it as well as I can. So it's too low level. All those things we just talked about are very complex. If you don't think they're complex, you're very wrong about that. It doesn't effectively leverage the security enables. I made this one bold. I don't know if you can tell. But that is a critical one. That is one that I'm really trying to emphasize, primarily for funding purposes, because I think that's going to be very important for large organizations. But also that package repository we just looked at is very tightly coupled. And I'll just try to give a brief description of what I mean by that is, so it's a giant repository of source code. It is one repository, one Git repository that has every single one of that giant number of packages that we just saw in that. And so what that does is it actually makes it very difficult to reference older versions, because every version that is currently specified is specified in the same structure all at the same time. So if you have a program that needs glibc like version 2, and then you have another program that needs version 1.4, then you have to literally go through the Nix packages history and find the specific git commit where glibc was that version, and then pin it. And that's also very resource intensive, because now when you actually go to run that, you have to pull both of those versions of Nix packages, and since Nix packages is so huge, like we just looked at, it's literally, I think just 2 versions is over 100 megabytes already. And then when you unpack it, it's like 500. So network-wise, it's very restrictive, and it sort of makes it very difficult to do the exact thing Nix was designed to do, which was to decouple dependencies, which I think is kind of ironic. And so because of those things I just talked about, it's kind of slow and heavyweight. Like I said, the language is fairly complex. And the big thing, the thing that I'm trying to solve is usability. So there is no abstract interface. So these two, the first and last point, kind of coupled together. Usually when you build a complex piece of software, you want to have a higher level interface that is easier for people to understand. And all of the complexity is sort of hidden behind that interface, so you can just do what you want to do. Nix is not like that. So you have to deal with all of that complexity we just talked about in order to be able to really leverage Nix. And I think I have another demo here we could do real quick. This sort of oh, or did I delete it? Uh-oh. Come on. No, it's here. Okay. All right, so I have Nix packages checked out on my system. There's the path right there. So these are some of the recent changes that people have made directly from the Git history. So I had it search for Python-specific changes, so we could kind of focus in on why this is a problem. So these are various Python packages that have been recently updated here. So like I said, everything depends on that one commit. So we have this coupling problem that we need to express. So we have our mix expression, this is where we're telling it which version of mix packages we want to use. So we give it, you could use a branch name or you could use an actual commit. But what if you need Python 3.10 for project A and 3.11 for B? How are you going to do that? You can't because the versions are tightly coupled to that one checkout, right? So you're stuck with whatever version Python is at. Now you can, like I just said, you can specify 2 different versions, right? But now you have 2 copies, which are hundreds of megabytes each when they're unpacked. It's complex to manage because each one of those is going to have its own chain of dependencies, which is going to be a lot more data to deal with. And it's a maintenance nightmare. This is really the thing that I don't think that the mixed community has fully grappled with. They just keep trying to brute force the maintenance of this thing, and it's not really working. And I'm trying to convince them that we need an entirely different model if we really want this to. And it is sort of becoming a problem because Nix, because of the giant number of packages, is becoming kind of mainstream, kind of. A lot more people are becoming aware of it. And because of these problems, in my opinion, it's not really ready for it. So a lot of people are having very negative impressions. And it's a real shame since it solves a problem that no other tool has really solved in such a way as we've sort of tried to demonstrate here. So yeah. Everything, I think I already said all this, so we can probably try to just move on a little bit. So what are atoms? I'll give a brief demonstration, but the high level is it's a proper package abstraction. So instead of having everything as a derivation, which is very nice for tracking your dependencies, but it creates this sort of granular structure where it's very difficult to sort of zoom out and be like, okay, but what package is this actually? And what version is it actually? And how do I know between all, like if you make one little change, it changes the hash, right? So how do you distinguish development changes from actual release versions, things like that? There's no way to do that. Next. So Atom creates an abstraction. I won't go into too much detail, but the important thing is that it maintains the cryptographic integrity. So basically, you give it a name, and you can use Unicode, and that name is combined with a cryptographic hash of the repository. And how I do that is sort of an interesting technique that, as far as I know, nobody really does, but basically all I do is, because the Git repository is a Merkle tree, like a blockchain, for example, you cannot modify the history without making it very obvious. So because of that, I go all the way back to the very beginning of history, and use the very first commit as the identity because that commit can never change or everything else will change. And if everything else changes, you don't really have the same project anymore. So that's how I sort of give it a nice abstract identifier that we can sort of work with and gives us something solid to be able to be like, what package is this? And to a user, they can just refer to it by name, version, but under the hood, it still has a very strict cryptographic identity. It's going to be a lot more efficient, and I'll get into that a little bit. It's got version resolution support, so it has an actual version abstraction that you can actually use to resolve different versions and solve the dependency problem that we talked about. And then it's decentralized. So the current iteration of Atoms is built on Git, and Git is decentralized, so we basically get the decentralization of Git for free, which gives us no single point of failure. And I think one of the important things that I didn't put on here to point out is that one of the reasons developers really love Nix is because you are building your code directly from the source. So that centralized registry problem we talked about with like JavaScript environments, if you've ever used NPM, anybody? I'm sure you have. So you are literally pulling all of your expressions directly from their actual source code, so there's no in between, there's no middleman that can inject some random stuff. But the issue there is, like we showed, it's very tightly coupled, and so Atoms basically take a way to still do that, to still reference the exact source code directly from the Git repository, but in a way that you don't have to pull the entire Nix packages repository every single time you want to reference a different point in history. And I'll try to give an example of what atoms actually do.
Side question on that initial commit hash.
Yes.
I frequently will do ones where like I might get ignore file that I always use, dump it in, do that on an initial commit on one, thing I'm working on, and do the
Yes.
same thing on the other. So in theory, they both have the exact same file structure as their
Yeah,
initial
exactly.
commit. Is there like a package name that goes into it? I've never looked at like what that first hash.
So
is.
I
Is it
have-
files or is it more?
I do know, I'm aware of this problem, and so my current iteration of code does not address it, but I've thought about it. I have a working architectural draft of how I can kind of start to solve it. You can inject some kind of entropy. It gets into a whole like ownership model that I have now of like how to manage keys and ownership using cryptographic key pairs and things like that, which is way beyond the scope of this talk. So.
I was just curious, because I know it's lazy coding on my part, but it's usually like.
No, but it's
get
common,
more
yeah,
file
for sure.
and-
No, Git is file system based.
That's what I.
But the other thing though, Git does help a little bit with that because the commit itself, it has a timestamp and depending on what commit message you use. So if nothing else, at least it'll be at a different time, which will affect the hash.
Yeah, now I have to create little projects at the same time to mess with you.
All right, so atoms are published packages that can be discovered and resolved, unlike Nix packages, which are tied to Nix packages. They are decentralized thanks to Git. They are referenced by version instead of derivation hash, so you can actually create a proper version abstraction. And then, like I said, they have a unique, unambiguous identity, so you still retain the benefit that Nix offers you, but you don't have to think about it. It's under the hood. So this is going to, I got to put in my SSH password. The script is going to actually ping a repository. Oh, come on. So this pings one of my repositories where I have some atoms published. And these are, it's pinging the actual Git server where the source code is stored. These are called Git refs. This is how Git, typically you resolve things from a Git remote repository. Usually it's a branch name, so I do something a little bit different here. Instead, I give it a very well-defined structure. So it's under the atoms. This is the name. This is that ID I was talking about. And then a very specific version for that thing. And then it's pointing to this commit here. But the interesting thing here is that this is not a commit from the history. So in order to explain how it really works, I have to explain like low-level details of Git. But essentially, it's pointing at just that. So if you have a giant repository like the packages with thousands of packages, right? It's pointing to just the directory inside of that has this app. So instead of referring to hundreds of thousands of files that we don't need, we only want this one app, we can just pull the directory that is relevant to that application. And so by doing that, we can create multiple different versions. I only have one version of each here because it's just for demonstration, but you can have like 20 different versions here, all referencing a different point in history, and you don't have to download Nix packages 20 times. So that's big. That's the big efficiency enhancement.
Does it change subdependencies? So if you include, GCC.
So that is, I do want to do a full-scale deep dependency, transitive dependency resolution. Right now, it's just resolving direct dependencies. But I do have a scheme for that. I need to implement some more low-level Git code. So I'm using a library in Rust called Git Oxide, which is like a Rust implementation of Git. And so I've already implemented a few things like to query this with my tool. I had to implement a bunch of low-level query code. But it works very well. It handles Git authentication and everything that you would want it to handle. So it works just like Git, but it is efficiently purposed for what I'm actually trying to do with Git, since you can't actually do this easily with the Git CLI. And then also for user-facing concerns, this is the big thing right here. You can reference atoms by just a simple identifier. Right here on this side of the colon, these are user configurable aliases. So instead of having to type out github.com, you can just put a little alias in your configuration and just GH will resolve to github.com. This is that repository we just looked at. And then : this is this atom right here, and then I probably should have put an example, but you can put an @ symbol in a version to specify either an exact version or a semantic version request, which is like a range of versions, and you want to find the highest one that matches. And so I didn't really give an example of the Nix CLI, but this is a giant improvement over the Nix CLI. You just have to trust me on it. I did kind of steal this idea a little bit from Nix Flakes, if you guys are aware of what those are. But Nix Flakes hard codes these aliases, so there's only like 5 of them. These are totally user configurable, and in order to avoid breaking downstream, they are only for your system. When they actually get put into the dependency tree, it resolves to their full address, so that somebody who pulls it doesn't have to have all your aliases. But yeah, the idea is that you can actually work at the level of abstraction that you want to, which is packages and versions, instead of having to think about all this complex cryptography. And then obviously, we talked about lock files a little bit. So this is usually how a locked file works. This is the atom manifest right here. Now it's a TOML file. If you guys know what the TOML is, it's kind of like a more concise way to write JSON. Basically the same thing. The important thing is that it's static. There's no programming going on. It's literally just a description language. So we're giving our atom a version. It has to have a version because that's the core abstraction. This is how you specify decentralized dependencies right here. So we create package sets. This first package set is company atoms pointing at our company right here. And there's only one, but you can have mirrors. This is the decentralized aspect. So public atoms here. These 2 repositories will be checked at runtime to make sure that they are actually the same repository. So in that way, you can have sort of a fallback mechanism, and you can pull atoms from the same repository that's hosted in different places. And the way that you do that is you literally just say, I want my dependencies from company atoms, which is going to come from here. And then this right here is a semantic version spec. So anything greater than 2.1, get the highest version. That matches that doesn't go over version 3, essentially. So we get a couple atoms from there, we get a couple atoms from the other source. And if you've used, anybody has used Rust, this is sort of inspired by Rust. Rust is not decentralized, so there is none of this going on. But the format here is very concise. I like this about Rust. You can just sort of specify a name and a version when you're done. So what that looks like when we actually resolve it. This is an example of the actual lock file. So we have an atom. This is the name we specified. This is the exact version that it actually resolved. And then this is its Git, those Git hashes we saw earlier. And then this ID field is sort of that ID I was talking about. So this ID that's calculated here represents that package. And so it doesn't change with every version. It's a constant identity for that package. It's like a person, right? You as a person, you change over time, but you're still the same person. So this package changes over time, which is declared by the version in the revision, but its core identity is still the same. And there's a lot that you can do with something like that, because now you can make sense of what package is what in a giant tree of dependencies, even as the version changes. With Nix, you can't do that, since everything is a derivation. The derivation changes, you have no you have no machine level way of knowing that it's still the same package. You have to know that yourself, essentially. The machine has no idea. And so why does this matter? Like, basically gone over all this by now, but it's decentralized, which is a big one, in my opinion, especially as the world moves in the complete opposite direction. Familiar interface, if you've ever used a package manager, it's sort of inspired by language package managers, and the term package manager is kind of overloaded nowadays because you have the system level package managers like app that we talked about, but then you also have package managers now for like programming languages themselves, like NPM is an example of that. And so Eka is sort of like, I was trying to think of what is a good word for it. It's sort of like a meta package manager because it does both. Right, so you use it as sort of a system package manager where you give it a specific package, but it handles dependencies the way a language package manager typically does. And like I said, it uses Nix as the backend now, but it's abstracted. Does anybody know what Geeks is? Got one. So Geeks is is a fork of Nix that happened like probably about 10 years ago now. And they use an entirely different language. It's entirely different, but it still uses derivations under the hood. So the idea is that I've abstracted everything enough, or I'm trying to keep it abstracted enough that you could in the future use a different backend. If something like GIX becomes dominant, then we can just swap it out on the back end and still use our tools. And yeah, like I said, we have actual human understandable identities for our packages now.
Call it a software aggregator.
Yes, and as someone who has worked at large organizations that were very excited about Nix and very positive about using Nix, I can tell you that it's very difficult to scale. So this last one, it's great for, there's a lot of individual developers that love Nix and they don't complain at all about it, but when you try to scale that up and use it at a large, any sort of, like I worked at IOG, which was a global organization. I don't remember how many employees, but it became very painful to the point where several of the projects stopped wanting to use Nix, and then it became very complicated because some projects were using Nix and some projects weren't, and it just created a huge problem that didn't have to exist if we had better abstractions. So, any questions about atoms?
So an atom can be a package or like an entire directory of packages, right? Like
Yeah.
it doesn't necessarily, like when I think of a package, I'm usually looking like I use Arch primarily, so I'm usually either hitting, see if it's in the Arch repository, or I'm going to the AUR for something that I know is not going to be there.
Right.
But it's just usually a package. So even though it's going to check out, and it's going to look at and install dependencies and everything else. So is it like taking, in essence, all of that in a thumbprint and then putting the hash on like everything? Like
So it goes into, you've used the AUR, right? So have you ever like looked into how the AUR is structured?
It's really weird.
Yeah, so
Yeah.
every package is basically its own repository.
Right.
And it's kind of like that, except that it's not split into separate repositories. The way Git works under the hood is it has 4 different types of objects, but there are 3 that really specify how files are laid out.
Okay.
So there's the blobs, which are just the files themselves. Those are hashed, and that is their identity, so you know what that file is. But the one that we're using in Atoms is the tree object. It's basically like a directory, but it's a cryptographically specified directory. So it's basically, these are all the blobs. These are the name of the blobs. So it's describing a directory tree.
So it puts the hash on the directory itself essentially, but not every
Yeah, so
file.
basically we detach the commit from the history, and we make a new commit that points at the same tree, but just isolated from history. There's nothing else in it.
I see. Okay. That starts to make more sense.
Yeah.
Okay.
Sorry, I probably should have explained that better too, because that's
No, that makes sense.
And then, so Eka is the CLI tool. It's actually a Sanskrit word. It means unity. And so that's kind of the core idea or the core philosophy here, is that we're sort of trying to bring everything together that we want to do and solve problems that we've had for a long time. So yeah, like I said, it's a high-level interface to Nix. We'll just do a brief demo of what that actually looks like. And this is running the actual code that I have written. So we're going to actually create a new atom, and we're going to resolve some dependencies. And it worked yesterday, so hopefully it still works because I made some changes today. All right, so we're going to see a real quick workflow. So this is how you specify the repository. The way it is right now, we make a simplifying assumption that the repository specifies a package set. So basically everything in the same repository is part of the same set. And this is a set in the mathematical sense because every single atom inside of the set is unique based on that cryptographic identity. So this is the one in my repository now. We only have one package. This is a Nix expression that actually parses the log file. That's the only package I have in here right now. You can have some metadata to kind of give it some information. This is going to be useful when I start to build a backend so that I can sort of categorize and make it easy to query. But that's what I have on disk right now. And I have to put my password in again. because my YubiKey isn't working. All right, and so here, I did not explain this. So this is that initialized state that I was talking about, and you asked about. This right here is the very first commit in this history. So in order to not have to compute that over and over again, and if you're referring to it remotely, you can't compute it because you don't have the repository. We set a Git reference to that so that you know what it is, and if you need to verify it, and I'm going to have verification tools and trust levels and all that stuff, but you can easily pull the source and just verify that this is actually true. But this reference is protected, so you can only like a repository admin should be able to modify it. And that has to exist to publish atoms, so you can work with atoms without initializing the repository. But if you actually want to share them and have other people use them as dependencies, then you have to initialize it. So now we're going to run the commands to create a new atom here. And it was successful, so we're doing good so far. So we did echo new demo app. This is the actual log output. So we made the new atom with this label at this path. And this is the full file path right here of the set that we added it to. And now we're going to look at what we just created. So Echo just created this file right here. It's a very basic atom package name that we gave it. It starts at version 0.1.0 by default. This is not super critical to understand, but this is what's called the composer. So this solves a problem that I have with Nix flakes. If you're not a Nix user, then it's not super important, but essentially this is a way to specify how you actually want to import your expression. So if you want to use my module system, which is tailor-made for atoms to work well, you can, but if you want to use something else, you want to import a flake, you can write your own composer, download it, and use that instead. So, and then I think we made a log file. Yeah, so because that composer is a remote dependency, we resolved the composer. It's at version 0.4.2 right now. And this is the set that it comes from. So this is the repository ID. And this is the actual Git revision that we're locking it to. And I think that's about it right now. All right, so now I just ran a command to add some dependencies from that demo repo I showed you earlier. And they worked. And then now I'm going to run a command to add a legacy Nix expression that is not in the atom format. So because atoms are brand new, if you actually want to use them, then you're going to have to interact with legacy Nix, unfortunately, at least until we build up the ecosystem. So I'm going to add Nix packages as a dependency. And then we're going to see what that looks like from here. So we can see that Eka updated our manifest for us. So it added the new sets. And it added the two dependencies we added. So you can do this by hand, but you can also do it from the CLI. And then here is the Nix dependency. So since it's not an atom, it's in a different format. So it's under direct dependencies, which are just specified by, very similar to the way Nix flakes works, just the full URL and the Git reference. And there's some cool stuff you can do with that, but I won't get into it.
And so Echo, the program, is generating the...
Yeah, these are all files it just generated.
Okay.
And then so this is the lock file it just created. So now it's locking everything. So this is all the information. This is all the cryptographic identities of all those things we just resolved. And yeah, actually it's important to point out too that the sets up here are specified by their identity as well. So when you have the set here, you can say, oh, okay, that comes from there. This is a legacy thing for Nix because Nix doesn't know how to resolve mirrors right now. I'm trying to push upstream.
That was my question.
But yeah, I'm also banned from Nix, so it's kind of hard to influence upstream right now. But we can get into that later.
That's the third part of your presentation.
Yeah.
right?
Although I did have a nice little meeting with some of the upstream guys last night because I think they're getting tired of all the political nonsense, but yeah. So publishing, we are not going to demonstrate because in order for publishing to actually be reliable, you have to actually commit the changes. So I don't want to commit the stuff we just made, but essentially you just run echo-publish, point it at the atom you just made. It'll verify that it actually exists in the Git history. And the important thing is it will publish it from the Git history. So if you have local changes on disk, it's going to ignore those. It's going to read the version from the manifest and pin it in that ref format we saw to that version. And yeah. And then yeah, once it's published, we can add dependency. We can add it as a dependency as we did in our little demo. Yeah, so that's this is enough to actually start using Eka, and this is was all really completed like 4 days ago. So it's been a long time coming.
Are you the sole contributor, or sole, are there? Yeah,
There is one other commit from one other person, and the rest is me. So yeah. But yeah, it's taken a long time. We have a whole community, like John Ringer. If anybody's used Nix, you probably heard of John Ringer, but he's working on another tool called Eka CI, which is sort of a CI system to make managing a large Nix repository more efficient. And so we have a lot of interest. We have like 500 or 600 people on our Discord right now. But since we're building entirely new tools, we have to like get to the point where they're usable. So now I am at that point. Obviously, there's still edges, probably still bugs, things like that. But at least I need to write more documentation now. But once people actually understand how it works, we can start using it and seeing how people like it. So, and I think that's the gist of it. I can just briefly talk about what I have planned. So the whole reason I designed Atoms was because I basically got fed up with Nix and I asked myself the question like, okay, if we didn't have to deal with all these pain points, and you could just have the perfect system that does something like Nix, what would it look like? And so I came up with this theoretical idea called EOS, and then I sort of worked backwards and tried to figure out what would you need, and that's what would you need in order to develop this, and that's how I came up with that. But essentially, because we now have these cryptographic identities, you can create a chain. And when I said earlier, the Nix CLI is very low level. You literally have to evaluate a Nix expression to get your package. So if the expression doesn't evaluate for any reason, it's broken and you can't use the package. With EOS in the future, you will be able to actually have a concrete cryptographic chain from the atom we have, the version, its atom identities that EOS will be able to index in the back end from thousands and millions of different repositories. And then you can create a chain from that to the revision all the way to the final package so that you never have to run any Nix at all. You can just grab your package like an actual package manager is supposed to work. So that's the high level idea, but yeah, that's all very, theoretical, so not worth going into too much. And so what have we learned? There is a path forward from Nix's inefficiencies, in my opinion. I think I've proved it to myself at least by now. The decentralization aspect is important to me. I have a lot of ideas, including a new document that I just drafted, was working on today. Sort of get into that, but that's a whole other talk. But basically, think of something like, it's not really blockchain, because it doesn't work like a blockchain, but something decentralized like a blockchain, but for distributing software, essentially. So we want to basically speak to developers at the level they're actually used to speaking at, which is versions. So, any questions?
I have a question. Have you run into any sanity check quirks by any chance with all this?
Any what?
Sanity check quirks?
What do you mean? Like, give me an example.
For example, like a mirror just not existing anymore or anything like that.
Yeah, so that's the point of having multiple mirrors, is that if some of them go down, you can still resolve your dependencies. So the way that it's actually implemented, I was actually pretty happy with. So my first iteration was very difficult to work with. And usually when you have something difficult to work with, what I've learned is that you need to rethink your data model. So that manifest format we looked at, it used to just be like a very centralized manifest, very similar to the way you might work with like Node packages or Rust packages. But then I realized trying to take a decentralized format and stuff it into a centralized format is causing me a lot of problems. So by creating this sort of abstraction of mirrors and sets, I was able to make the implementation way more efficient. So basically it resolves all those mirrors up front asynchronously, so it does it all at the same time. It starts processing them even before they're all done, so it's just doing it literally as fast as it possibly can. And then it verifies any conflicts right then and there so that you won't have any consistency issues. So if two repositories point at the wrong source, it will tell you and fail and be like, you have to change this, you can't have this. So yeah, thankfully all of that has been worked out. And that was one of the hardest problems was, especially any decentralized system is a lot more complex than a centralized one because you have to maintain a bunch of different invariants to make sure that things still make sense. So solving all those problems was a big part of actually putting this together. But yeah, there's a ton of different invariants. Like the important one is that every atom in a set must have a unique name because otherwise there would be no way to disambiguate them. So I enforce that using some data structures that make it impossible for that to happen, things like that. So yeah. Anything else?
So this is the idea from this came from the frustration from the NixOS like package manager, but
Yeah.
really though it's portable in the sense that it could be applied to non-NixOS.
Yeah, so one of the angles I'm going to try to push for now that I have something actually usable is I want to sort of decouple atoms a little bit more and make it an entirely separate thing, which it already kind of is, it's a library, but I want to decouple it even a little bit more so that it can be used as a generic packaging format, totally independent of what ECA is doing. Like for example, I love Rust. I've written ECA in Rust, but the thing that I don't like about Rust is its packaging format. So a lot of the things that I designed ECA around was like, how can you make something that is like what Rust is trying to do, but that doesn't suffer from all of its problems? And so one of the things I'm thinking about doing is drafting an RFC to the Rust community to support atoms for crates. Because one of the things people hate about the crate format right now is that it's a global namespace registry. So if your name is taken, you're shit out of luck because it's global, like literally the entire world. You can never have that name again, which is only amplified by the fact that people just go and take a name and then they don't even write software for it. So it's just taken forever and you can't use it. With a global ecosystem like Rust, that becomes a bigger and bigger problem as time goes on. So it might become useful to actually solve that problem and just package your crates with Atom. And then you can use ECA to pull those in and actually build something useful with it. So, anything else? Who here knows what the hell I'm talking about?
About 40% of our users.
Awesome, that's worth something. I'll take it.
I mean, so we're over on time.
Yeah, sorry about that.
No, that was great. I thought that was a really good conversation, but if there's no more questions, we will wrap up for the evening. So I think we're probably done. So.
Yeah, go ahead.
Yeah, I was going to ask the same thing because Go's done a lot of
I did actually when I first started. I looked at like deep dive. I don't remember a lot about it, but
and they've had a lot of issues. I'm not happy with some of these stuff. What's that? Yeah, modules. There's been a lot of issues with modules.
I did actually sort of take inspiration from the fact that you can specify dependencies by their Git subdirectories.
Yeah. Oh, did that come from Go?
Kind of. My first iteration was exactly like that. And then I was like, wait, I don't want the file system to be part of this equation, so I abstracted the file system out of it.
So with this, it's decentralized to the point, so if you have your own Git repo set up, right, you could basically create your own packaging system that relies on that.
Right, and then somebody can clone it and then offer a mirror, essentially.
That's pretty awesome.
Yeah.
It's like a bit of like a large medium business, if they wanted to employ stuff with atoms, like they could have their own secure internal repos.
Exactly, yeah. And that,
Or an offline repo.
yeah, that goes back to his statement about secrets, actually. So you could have like a secrets atom set that is not exposed publicly, and for any sensitive information, you could pull atoms from there, and then have like your public stuff in a different set. So. Cool.